All right, let's check. Perfect. Okay, so I'm Dutika Vats. I'm a postdoc at the University of Warwick. I'm going to be talking about the R package MCMCse that has some work from my dissertation and does output analysis for Markov chain Monte Carlo. The package actually was started by James Flegel and John Hughes, and I started in 2015, and then Ning Dai has recently contributed to the package. All right, this is probably the largest audience I've ever had, so not worried at all. Okay, so what does the package do? Well, it does output analysis for Markov chain Monte Carlo. So of course, I'm going to have to do a little bit of review about MCMC, just hopefully enough so that you understand what the package does. But in case if you already know about MCMC or you really are not interested in some of the math and the details, then you should still wait and sit around, because the highlights of the package are that you can do univariate and multivariate standard errors for MCMC. You could also calculate something called the multivariate effective sample size as opposed to univariate effective sample size. I'll talk about that. And also, you can find out what is the minimum effective sample size required for your MCMC problem. And that you can do before you start simulation. All right. So what is the MCMC story? So imagine there's a distribution, capital F has a mean theta, and you go and draw IID samples from that distribution. Then you can estimate theta using that sample mean. Right? And so in R, if this is p-dimensional and you save your samples in a matrix, you can do this by column means. Right? But I'm a statistician, so I'm more also interested in assessing the error, because every time you do this, you're going to get different estimates. And so I go to my favorite theorem, which is the central limit theorem, right? And say that there's going to be an asymptotic error, and that's the covariance matrix lambda. And I want to be able to estimate that so that I understand what's the error in my estimation, right? And in R, we would do that using COVE, okay? Now, this is not the MCMC story. This is the Monte Carlo story. What is the Markov chain Monte Carlo story? Is N is when the distribution F is bad. It's difficult. It's not well behaved. It is annoying, okay? And that might happen often in, let's say, Bayesian settings where you have a posterior that you don't know completely. And so instead of drawing IID samples, what we now do is draw x1, x2, xn, which form a Markov chain such that the stationary distribution of the Markov chain is your posterior distribution. Now, there's lots of theory behind this whole sentence, but what it essentially means for the purpose of this talk is that your samples are correlated, right? So we're very far from the world of IID sampling, right? You have serial correlation. You have correlation everywhere in the sample. Okay, but the usual thing actually still does work. So you can still estimate theta by the, whoops, that's a typo. That shouldn't be a G. That should be just X. You can still estimate theta by the sample mean. And you also may have a CLT. In many situations, you do have a CLT. But the covariance matrix here is no longer the lambda. It is sigma, which is different from lambda because you have the correlation in the samples. So the variance of the sum is no longer the sum of the variance because you don't have IID sampling, right? And estimating this guy is hard. It's very difficult, and that's where you're going to want to use MCMCse, okay? And so MCMCse stands for Markov chain Monte Carlo standard errors, and actually estimates either the whole matrix sigma or just the diagonals, depending on what you want to do. Okay, so of course I can give you a big Bayesian model and try and sample from the posterior, but I'm just going to sample from a bivariate normal so that it stays simple. So assume that we don't know how to sample from a bivariate normal. We don't know that the package MVT norm exists. So the mean of this normal, is 2 and 5, and the lambda, as in the covariance structure of this normal distribution, is unit variances and then 0.8 correlation. This is what the bivariate normal looks like. Of course, here we have the luxury of knowing the mean 2 and 5. Okay, then that's going to help us in trying to demonstrate how this package works. All right, so I'm going to kind of want you to remember lambda a little bit. So just remember that you have unit variances on the diagonal and correlation being 0.8. All right, that's your homework or talk work. Okay, so I use a random walk metropolis sampler. I will not tell you how I coded the sampler. You could use JAGS or RStan or whatever you want, as long as the output from the MCMC is a matrix. So if it's not a matrix, if it's some other object, you can convert it to a matrix, okay? But essentially, I somehow sample from this bivariate normal. But I draw an MCMC sample, so I have correlated and non-IID samples. All right, so the way I sample, I obtain 10,000 samples, and this is the function that samples it. This is not in the package. This is just me trying to demonstrate the function of the package. And that object is now stored in out.rwm. The question is, how did I choose this 10,000? Are these 10,000 samples going to be enough? So that's the question I'm going to answer using MCMCse. Are the 10,000 samples going to be enough for this problem? Okay, so all right, so let's see first how a Markov chain would look like. Hopefully this will work. Right, so it's starting at 0, 0. So the red dots are the values of the Markov chain sampled. So it's starting at 0, and then goes here, and then here, and then here. And you can see it eventually is concentrating near the bivariate normal contour that's been plotted here, right? So you're eventually getting draws from the distribution, but they're correlated draws because each draw depends on the previous draw. So this draw depends on this draw, and so on and so forth. So there's correlation. Okay. All right. So the output of your Markov chain should look something like this to be used for the MCMC package. It should look like a n, as in the Monte Carlo sample size, times p, the number of components in your distribution type matrix. Right, so this is, let's say, the first sample drawn, this is the second sample drawn, third, fourth, fifth, sixth, and so on. Like I said, to actually find the estimate of the mean, I can just use column means on this, so I get 1.9 and 4.9, which is very close to 2 and 5. But again, if I do this many times, these numbers are going to be different, and I don't really know what the standard error on this is. And whether, because here I know the truth, but generally, I won't know the truth, right? So are we close enough now? Okay, and this is where you're going to load the library MCMCse. So you load it, and then you use the function mcse, which is Monte Carlo standard error, and this calculates univariate standard errors. And so I now do this just for the first column, just for the first component where the mean is 2. Right? So the estimate is 1.9, which is fairly close to 2, and the calculated standard error is 0.0338. And so what does this standard error come from? Well, you have this asymptotic covariance matrix sigma. Its diagonals are sigma square. To calculate the standard error, I take the square root and divide by the number of Monte Carlo sample sizes. Right? So I do sigma over root n. Right? Like you would do, say, in a t-test. Okay. So it calculates that particular standard error. But in many Bayesian problems, many of these distributions are too complex in high dimensions. And so we might want to do this for many different components, not just the first component. And so you can use the function mcse.mat, and it'll give you a column of the estimates and a column of the standard errors. Okay? Now, here's the thing. So this SE over here is sigma over root n. I multiply by n, and I square. That should give me sigma squared, as in the diagonals of the sigma matrix. And that is 11.4 something and 11.9. Compare it to 1, which was the variance in the target distribution, the bivariate normal, right? The target distribution has variance 1, but our Monte Carlo variance here is coming out to be 11. So it's very inflated. And why is that? And but that's because of the serial correlation. It's because of the fact that we have correlated samples, right? So if I look at ACF plots for the first and the second component, I see that there are positive and significant correlations over and above, let's say, lag 20. And all of that is accounted for when you use standard errors via MCMCse. It estimates all of that consistently and then gives you an inflated estimate. Sorry, the estimate is consistent, but it's inflated because of the correlation structure. Okay. Now, the original question that I'd asked was, are 10,000 Monte Carlo samples enough for my problem? I haven't answered that. I've just given you an assessment of the error. One way to assess whether you have enough samples or not is by this concept of effective sample size for Markov chains. So effective sample size effectively tells you how many IID samples is this correlated sample equivalent to for your problem, right? So if I have 10,000 MCMC samples, well, how much power essentially do they give you if compared to an IID sample, right? So the way effective sample size is usually calculated is that depending on how many ever components you're estimating, it calculates effective sample size for each component separately. And the way it does that, it multiplies n by the ratio of the variance if you had done IID sampling and the variance from MCMC sampling. And so because the bottom part is inflated, this guy is large, and it brings down the effective sample size, right? And so for our problem, remember that we got 10,000 Monte Carlo samples, and the effective sample size turns out to be around 860, okay? And that's because effectively the sample size has come down because we're dealing with correlated sampling. Okay, but here's the interesting thing. We have two CLTs. We have a CLT from IID sampling, and we have a CLT from Markov chain sampling, and both are multivariate. So if you have multivariate CRT, why in the name of God are we doing univariate effective sample size, right? Why are we doing this for each of the components separately? And what is the loss if we're doing each of the components separately? And the loss is that we're not accounting for all this cross-correlation between the two components. Recall that in our target distribution, the correlation between the two components was 0.8. So the estimated cross-correlation at this lag 0 is 0.8, right? And so that part is not accounted for, but also lag correlations are not accounted for across components, okay? And we want to be able to capture that so we have a better understanding of what our effective sample size is. And that's what happens using the function multi-ESS, which is multivariate effective sample size. And instead of using the ratio of just the diagonals, it uses the ratio of determinant scaled appropriately, all right? This top part is estimated by the package using the cov function, the covariance function, and the bottom part is estimated using the function that's in the package, that's mcse.multi, that actually uses some HAC estimators and something called the batch means estimator. I'd be happy to talk about that separately. Right, so the multivariate effective sample size for this turns out to be 1,200 from a Monte Carlo sample size of 10,000, okay? Again, I really haven't answered the question, are these enough samples, right? I know that I have 1,200 effective samples, but is that enough? I don't know. All right, so that's the last question I'm going to answer. So how do we know that if we have enough samples? Well, there's this function called min-ESS, and it essentially does what we do in t-tests, in one sample t-test. If we want to make a confidence interval of some half width, and we want to make, let's say, 95% confidence intervals, and we have an estimate of the variance, we can find the sample size, right? That's our stat maybe 101 or 201. Similarly, here instead of a half width, we have a relative tolerance, and that's some epsilon, and a general value for that could be epsilon equals 0.05. And if we want to make 95% multivariate confidence regions, that accounts for those cross correlations, we need a minimum blank number of effective sample size where blank is filled by the min-ESS function. So the min-ESS function, I put in the number of things I'm estimating, that's two component means. Epsilon is 0.05, and my significance level for the confidence interval is 0.05, and I need at least 7,529 effective samples. So I have to simulate my Markov chain until I get those many effective samples. The interesting thing is that this does not depend on our Markov chain, this calculation. So you can, before your problem, find out what you know what your P is, choose maybe default values or more fine-tuned values of epsilon and alpha, and you can figure out what your minimum effective sample size is. Depending on your Markov chain, it's going to take longer to cross this min-ESS threshold, right? If it's a slow Markov chain, it's going to take longer. If it's a fast Markov chain, it's going to reach that threshold faster. So for my Markov chain, I went back and I simulated 80,000 observations instead of 10,000. Then I ran my Markov chain again, and then I recalculate effective sample size, and I get 7,919, right? And so now I know that I have 7,919 effective samples, which is larger than the previous lower bound of 7,529. So I overshot a little, but that's okay. I don't mind overshooting, but I'd rather not undershoot, right? And so you can conclude that with 80,000 Monte Carlo samples, my effective sample size for estimating the mean of this bivariate normal distribution is 7,900 for a relative tolerance of less than 0.05 in order to be 95% confident. This is, of course, a mouthful, but this is exactly what we write down in Stat 101 when we're trying to describe our results, right? And finally, I end with my estimates, which turn out to be 1.989 and 4.99 for my bivariate normal, which is 2 and 5, which is close. All right, so to conclude, the key thing about this package is the min-ESS function and the multi-ESS function. And the min-ESS function can be used before simulating your Markov chain. And I recommend using multi-ESS over ESS because the cross correlations really need to be understood and be accounted for. Because without that, you're just doing univariate analysis, which in Markov chains does not really make as much sense. Now, of course, there's this really cool CODA package that's really famous for MCMC and does a plethora of things. It also estimates effective sample size, but doesn't use consistent estimators. It uses a bias-only univariate estimator. So we think that using these consistent estimators that also can be used in a multivariate way is hopefully going to be better. Now, the example I showed was only for the mean. You do it for other functions of interest. You can also do quantiles. And there's a vignette up, and the package I recently updated. And yeah, if you have any questions, you can let me know. Thank you. Yeah. Sorry, can you say that again? I didn't hear you. Yeah. Right, so the epsilon tolerance is kind of a relative tolerance based on the variance in your true target distribution, which in this case was that covariance matrix. So that compared to your variance in your Monte Carlo, Markov chain Monte Carlo sampling. So what you basically want is, because you can keep on reducing the standard error in your MCMC sampling if you get more samples, you want this error to be an epsilon fraction of the error in the true posterior or the true target distribution. And so that's what the error means. And so we've done some simulations and we've done a lot of work in this, and we generally say that epsilon equals 0.05 is reasonable, and if you really want to be sure, because if your problem is really super important, could save somebody's life, then epsilon equals 0.02 might be a better option. Yeah. Yeah. Yes? Right, so I kind of did not go over how I'm actually estimating. So the key thing about the package that everything somewhat depends on is estimating the sigma, and that's difficult. To estimate so we've coded the estimators, 2-3 different estimators, and we've coded them all in RCPP, so it's relatively fast. What I've been able to do so far is P equals 500, and the number of Monte Carlo sample size, which is generally the larger object, could be up anything above like 10 million. Not anything above, anything below 10 million. So a 10 million by 500 matrix, if you can feed it into R, you should be able to use the package. Yeah, that's the other problem, feed it into R. I mean, are we good in time? Yeah. Right. Right, so I personally don't do burn-in because I don't want to blindly do burn-in. If I look at my samples, it starts at 0, 0, and within 3 samples, it's in my area of high probability. So just to throw away 1,000 samples in the beginning without actually seeing what's happening is throwing away 1,000 really important samples. So the first 3 steps, maybe I could throw away, but hey, the Markov chain gets stuck in that. Hey, let me just introduce a little bit of exploration at the bottom. I don't mind that. There are 2 schools of thought on burn-in. One, that it's absolutely essential and you have to do it. And then the other school of thought is, hey, if you know your Markov chain isn't perfect, then don't blindly do burn-in. If you have a learned estimation of when you should do burn-in, then sure, go ahead. All right. Thank you.
Okay, thank you.